Hello my friends, in this video we are going to explore the basic of induction motors. To start with, let me play with you with an experiment. Suppose we have a permanent magnet hanging vertically on the top, and underneath the magnet we have a piece of metal, and the metal is made with non-ferromagnetic materials. Now, suppose the right now the magnet and the metals are in a stationary positions. So nothing will happen unless we cause some motion on either party. Suppose the magnet is moving to the right direction. So what is going to happen? Theoretically, if the magnet is close enough to the metals, then it will generate a moving a moving magnetic field. And by Faraday's law, the you will induce a voltage in this piece of metal, and the voltage is given by uh, minus d plus dt. And the faster you move, the higher voltage you will generate onto into the magnets, into the metal. And the EMF itself will in turn generate uh, another magnetic field in a way to oppose the relative movement of the magnets. So I better write down the important concept here. The back EMF induced in the metal will generate a magnetic field to oppose the relative movement of the movement of the magnet. So we have two extremes. Either both parties stop, or on the other extremes, the metal will be driven to motion, and this is a more likely scenario. So eventually, both stop. Both magnet and metal stop. Stop moving. So this is one scenario. And another scenario is both metal and the magnets will be moving. moving to right. Now, I'm going to show you a video. Now there's a magnet hanging on the top of the metal. So if the magnet is moving to right and left direction, and you will see that the aluminum cans is rolling as well. The aluminum cans is trying to follow the motion of the is trying to follow the movement of the permanent magnets. Aluminum is not ferromagnetic materials, but it is a conductor. So going back to the right box, uh, in this case, if the magnet moves, it is logical to assume that the metal will be moving to the right direction as well. So now we are going to take advantage of this phenomenon and build a motor. And this is the so-called induction motor. Suppose we have a cylindrical metal, and this metal is so-called rotor. And the motor is mounted on a shaft, rotary shaft. And now, uh, suppose the rotor is placed between two pieces of magnets, and the magnet itself has a north and south pole. So N, S here, and S, N here. If I don't move the magnets, nothing will happen. But if I move the magnet, say the magnet on the right, on the left side of the experimental setup, we will move it upwards. And on the other hand, at the same time, the magnet on the right is moving downward. So essentially, you are now creating a moving magnetic field. This one, the one on the right, sorry, the one on the left is moving upward. And the magnetic south on the right side is moving downwards. So eventually, according to the phenomenon that I have observed, we should witness a rotation in this rotor. And in this case, most likely the rotor will be moving in a clockwise direction. But the speed of rotation will be reduced. Now, suppose we have another scenario. We are not going to use the permanent magnets. We are going to use um, a electromagnet. And you have a coil winding the ferromagnetic material. And again, we are going to have something similar. We have something similar on the right, and the current is moving this way. Okay, so the current powering these two electromagnets is I of t. I of t. If I don't move the electromagnets, nothing will happen. We will generalize according to the right hand screw rule. I will have a north pole here and south pole here. And again, so we have a south pole here and north pole here. But without any movement of the electromagnets, we are not going to observe anything. Now, so this is the case. So no movement. Now, suppose now the I of t is a DC current, then nothing will happen, right? Let's write down. If I of t is a DC, and if the electromagnet, the coil is stationary, sta- nothing will happen. But what if I use an AC to power this electromagnet? The AC electricity will goes up and down. Uh, so now if IT is an AC, so what we are going to see is something is going to happen. We are going to witness the periodic changing of magnetic field here. And if I'm going to demonstrate to you in a pot, and the pot is like this, and this is the current, and this is I of t. And suppose this is the sine wave, and we know that at this point of the time, say t1, we will have a loft maximum here. And south maximum here. And this is T is equal to T1. And afterwards, after some time, then uh, the north pole and south pole here are not going to be maximum again. So if I don't have any special arrangement, there's nothing special. And the magnetic pole here, the magnetic flux here will go up, down, and up and down. You will induce a back EMF here, but apart from the back EMF, there is nothing happen. The rotor will remain stationary. But now, suppose we have uh, another pair of electromagnets, and this time the electromagnets are arranged in this manner. And again, we are powering the electromagnets with, with a coil. Okay? Uh, so, and the current that I'm going to apply to these two electromagnets, I mean the red one, is going to be I of t plus some phase shift. And this is most likely uh, some phase shift. Right? We don't know the phase shift yet, okay? So most likely, I will end up with something like this. So this is the timing diagram of the current. And when the time is T1, then we will have a maximum here. But at other times, the north pole, the north maximum and the south maximum will disappear. So for instance, at T2, where we have a maximum current for IT plus prime, the north maximum will be shifted to this position. And the south maximum will be here. So the original north will disappear. And the original south maximum here will disappear. And if I'm going to add one more phase, hang on a minute. Okay? If I'm going to add one more electromagnet here, and again, we are going to supply some current into the electromagnets. The current at this time is I t minus phi. So what we are going to see here is something different. Previously, we have something with a phase shift. Like this, right? We don't know the value, right? But now we are going to have something different, right? Uh, we are going to have something like this. And this one is so-called I of t minus phi. So now this way of powering the electromagnets in the uh, in the status, and we call this arrangement theta. Theta means there is nothing changing. Uh, the arrangement of magnets is so-called status. And when the time say reach this point, uh, and the time here is T3, let's say, and we have the maximum current for the blue phase. And in this case, at T3, the magnetic loft maximum will be moved to the new position here. And the magnetic south maximum, in this case, will be moved, will shift in position. This is the south. And this process goes on and on. So essentially, even without any physical movements of the electromagnets, you are now seeing the rotation of magnetic field. And this rotating magnetic field is due to the presence of this AC electricity arrangement. And this AC electricity is so-called free phase electricity. Free phase AC electricity. And with this in mind, you will have a rotating magnetic field continuously until you stop supplying the currents, the free phase current to the stator. So now the conclusion at this point is, if you have an AC and this is the polyphase AC. And if the coils are stationary, then the the magnetic field in the stator will be rotating as well. So now, this is a very important phenomenon, and Nikola Tesla discovered this. It will be rotating. In this scenario, the magnetic field is rotating in the clockwise direction. And you are going to see the rotation of the rotor to the clockwise direction as well. This is because of the observation we have seen. And this is the working principle of the induction motor. You have a stator, and in the stators, the electromagnets are stationary. However, if you power the stators, the electromagnets in the stators with a polyphase AC electricity, then you are going to generate a rotating magnetic field. And this rotating magnetic field will in turn drive the rotor into motion. And the rotor in this scenario will be rotating in a clockwise direction. And now let's take a look in the basic characteristic. The motor here is very funny. The motor is full of torque. First of all, when you power the electromagnets, then you will naturally end up with a change of flux, a time varying current. And if you have a time varying current, then you will have a time varying magnetic flux. And this time varying magnetic flux carry a lot of power. And suppose the power is P converted. Then because of the power, uh, then you are going to end up with mechanical action. And by Newton law, the the converted power is going to be T omega, where omega is the angular speed of this rotor. So eventually you can plot the torque as a function of the rotating of the angular velocity. And in fact, this is true. Uh, but the converted pole, but the P convert is not constant. And because of the non-constant of P convert, we end up with a very funny torque speed characteristic. So now suppose the rotor speed is omega r, and the vertical axis in this graph is torque. The unit here is Nm, and the unit here is say radian per second. The torque will start at the beginning when the motor start from zero velocity, And then the torque will come down briefly as the velocity build up. At this point of the time, we have a local minima here. So this is so-called pull up torque. Pull up torque. And the starting part is so-called start up torque. And after this local minima, then the torque will build up naturally, but not linearly. The torque will continue to build up as the velocity increases until it reaches a maximum. And the torque at the maximum here is so-called breakdown torque. And after the breakdown torque, if we continue to increase the speed of the motor, then we will end up with a linear correlations between the torque and, and the angular velocity. And the speed will be maximum when it is equals to the rotating speed of the magnetic field, the angular velocity of the magnetic field. So this is the basic phenomena of the induction motor. If you have any questions, please leave your question to the comments box underneath the video. And thank you very much for your support.